Hey guys, so for this Hughes View short, I'm going to go over a different mixture separation technique, which is gel electrophoresis. So in last class, we just wrapped up chromatography basics. So chromatography, as you recall, is think of kind of like having a big plastic tube in front of you, and then you pour beads into that tube, and those beads are modified somehow. They either have pores in them or they have functional groups on there on the outside of the beads, or you have covalently linked molecules to it. It just depends on what type of chromatography you're talking about as to how the modifications are on those beads. So that would be chromatography basics. But now in gel electrophoresis, we're essentially going to have the same gel and we're going to use it in different ways by changing either little things about the gel or the way that we compounds we can add into the gel. Okay, so for the gel though, it's a polyacrylamide gel. And so I want you to think of the gel as being like a big meshing network. So it's mesh-like. So there's pores and our proteins are going to snake their way through these pores. Okay, so obviously the size of that protein can affect how it can make its way through this mesh-like network. And also the charge on that protein, because gel electrophoresis is run in water against an electric field. So we put an electric field against across the gel, and so proteins will migrate differently in that electric field as well. So let's get into some examples of different types of gel electrophoresis we find are common in biochemistry laboratories. The very first type of gel electrophoresis technique I would like to go over is sorry, I'm trying to get my laser pointer. Native PAGE, which PAGE is short for polyacrylamide gel electrophoresis. Native refers to the idea that the protein is in its natural folded state. So, sorry, you're not going to denature this protein so it's this long strand of spaghetti. That's a different type of electrophoresis. But in native PAGE, we're going to keep the native structure, so the naturally occurring structure of your protein. Okay, so you can kind of see a setup here. So you've got the gel. So this little box right here is the gel. And then you've got wells. So that in this gel, remember the gel is like a mesh-like matrix here. You're going to have a solution that's above the gel and a solution that's below the gel, because again, you're going to have a power supply, and that's going to put an electric field on either side of the gel. So now our gel essentially is charged. Okay, so let's think about how proteins would run on a native PAGE gel. So if here's my gel here, this is just a picture of it. So I've got that positive electrode at the top. I've got a negative cathode at the bottom here. And then see, they kind of show it's like a mesh-like network. So how would proteins in their naturally occurring folded states run in this type of a gel? Well, just think. So smaller proteins are going to run faster, right? Because they're smaller, so they can wiggle their way through that mesh faster than larger proteins can. So, and then remember, we have an electric field across the gel. So proteins that are more positively charged at whatever pH you're running this at, those are going to run farther towards the negative cathode down here, right? So if we just compare small proteins, right? So the small protein that's really positively charged is going to run the farthest down the gel from the well. The wells would be up here at the top. And then the small protein that is slightly positively charged is going to kind of run, I don't know, it looks like about halfway, right? There's not like a tried and true, like proteins of this molecular weight are going to run this far. There's a lot of variability, but just relative to one another is how I want you to be able to think about these gels. The large molecular weight proteins, so the bigger proteins, aren't going to run all the way to the bottom, right? They can't weasel their way through the mesh material of that gel. So you're going to kind of see them more towards the upper end of the gel where they started. And just like with the small proteins, the larger proteins that are more positively charged are going to run further. Okay. So if these two proteins were the exact same molecular weight, right, the one that has more positive charge is going to end up running further. Okay, so let's now look at a different type of gel electrophoresis, and this is called SDS page, and SDS stands for, sodium dodecyl sulfate. So dodecyl is 12, it's a 12 carbon, here it is right here, 12 carbon chain, sulfate, here's the sulfate group, and sodium. So sodium is a counter ion there. Okay, so it's sodium dodecyl sulfate, and then page, polyacrylamide gel electrophoresis. So it's, again, it's kind of like the native one, except for the thing is that this molecule is essentially a soap molecule. And if you were to make an SDS solution, it would have bubbles on it. It's very soap-like. Okay, you've got this hydrophobic tail, this nice hydrophilic head group. So what you're going to see is that in your protein structure, usually the center of it's very hydrophobic. These hydrophobic tails of the SDS molecule will kind of force their way into the protein structure, and that's going to break it apart. Okay, so that's what denatures the protein. So essentially, it turns a nicely folded globular-like protein into a long kind of strand of spaghetti that's completely covered with these SDS molecules. And in fact, it's about one molecule of SDS binds for every about 2 protein residues or amino acids in that protein chain. So you essentially get this really nice, because of this, every 2 residues has 1 SDS molecule. So every 2 residues, it ends up netting 1 negative charge. So you turn your protein into this really negatively charged thing, and it has what's called a, where's my big like mass to charge ratio? Here it is. That's the big buzz phrase for SDS page gels, is it separates proteins based on their mass to charge ratio. Okay. And again, that's because for every 2 amino acids in the protein chain, 1 SDS molecule will bind. So so what you'll just see is throughout the gel is that big proteins that weigh a lot stay at the top, and small proteins that don't weigh that much go towards the bottom. Okay, so obviously in this instance, you'd have a positively charged electrode down here, right? Because all of these proteins are going to have that negative charge from that sulfate group on it. And then, so you have a positive electrode down here and the negative electrode up here, and you just run your gel and it just separates it solely based on size. Okay. And its fattest, biggest proteins are towards the top because, again, they can't make their way through that mesh-like structure quickly or as well as these tinier, smaller proteins. So here's kind of an example of some different proteins that were run on this gel over here. So on my y-axis, it's molecular weight. So that's how big they are, how many kilodaltons they are. And then on my x-axis down here, this is the distance it migrated in the gel. So how far it went in the gel. So the smallest protein is this aproteinin protein. And that way, that is about 6, I think it's 7.5 kilodaltons in size. Next, you would have lysozyme, which looks like it's about, I don't know. Is this like a log scale over here? What's going on? 10, that's 50, 40, 30, 20. I don't even know what the scale is on here. Okay, it's between 10 and 50 kilodaltons, right? But you can see that the larger the size, the less distance it traveled. Okay, so again, SDS page gels are going to separate based on the mass to charge ratio, and the biggest proteins are going to stay towards the top, and the smallest proteins are going to travel the farthest. End of story. End of discussion. So sample question, here you go. How would the following mixture of proteins migrate in an SDS page gel? So here's a couple different ones that I've made up. So I've got hexokinase, this is carbonic anhydrase, lyase, and RNase. And here's the number of amino acids they are. Okay, I have my gel over here. And usually when you run any gel, you're going to also run a molecular weight ladder. Okay, so this is the ladder. Or sometimes it's called a marker. And I have the corresponding masses with lined up with the bands that are occurring in this gel. So you're going to have to solve this question, calculate the mass in kilodaltons of each of these proteins first, and then just plot them over here where they are relative to the markers. Okay, so you have to recall a certain number up here in your head because I just tell you the number of amino acids there are. And remember that for every one amino acid, it weighs roughly 110 daltons. So you need to take the number of amino acids and you need to multiply that by 110 daltons per amino acid, and that will give you the molecular weight in daltons. Okay. Then to convert that to kilodaltons, you just move the decimal place 3 spots. So if you crunch the numbers for this first example, you would see that the mass was 37,000, it's like 850, whatever, rounded up. So 37,900 daltons. So that's just 37.9 kilodaltons. You do that for each of these. So take all these numbers and multiply it by 110 because, right, each one amino acid weighs on average 110 daltons. And you get these masses. So then now you have the numbers and you just come over here to your gel and you can plot those numbers. So 37.9, so 37, here's 32, here's 41. It's somewhere in between there. Boom, we'll just draw it there. 24.3, here's 23, there's 32. So it's a little above 23. 47 and a half, you find where that would go. Here's 41 and 53. It's about in the center there. And then RNase is 62.9 kilodaltons. So here's 53, there's 68. So you would put a band there to indicate that's the RNase. Okay, so those are the two types of gel electrophoresis. Here's some more. I'll go over a couple different ones here, but so remember we have native and then the SDS. So native is the native state of the protein. It's folded, it's like globular, it looks nice. And that separates based on size and charge. Right, just the higher ones are going to hang towards the top, the lower ones travel farther, and then the ones that are more positive are the ones that are going to travel more towards that negative electrode at the bottom. And then SDS page denatures the protein completely. So it's not nice and folded anymore. It's just kind of a long string of spaghetti that has all those soap molecules on it. For every 2 amino acids, there's 1 soap molecule. And then that separates everything just based solely on the mass to charge ratio. Okay, so moving on to another type of gel electrophoresis. This is called isoelectric focusing. Okay, so you take an acrylamide gel, but this time when you're making it, you increase the pH from one end to the other. So on the other examples, there's no change in pH. It was just all essentially at pH 7, for native page and SDS page. But in isoelectric focusing, you have a pH gradient that goes through your gel. Okay, you just purchase these from a vendor. I mean, you can make them in the lab, but why would you do that when you could just purchase them? It's a little tedious to do in the lab. Okay, so you have an increasing pH downside. You load your sample, so your mixture that's been buffered at about pH 2, so you know that it's almost all the functional groups are protonated on that whole thing. So your proteins are going to be very, very, very positively charged if everything's protonated. Okay. You apply a voltage, so you're going to have the positive electrode towards the top, the negative electrode towards the bottom. And the proteins are going to migrate through this gel until the pH of the gel is equal to their PI. That's the isoelectric point. And why is that? What does it mean to be at the isoelectric point? Recall that it means that you have an overall net neutral charge, right? So does a neutral object move in an electric field? And the answer is no, it doesn't. So what you see is these different proteins. So again, we have to think about those functional groups ionizing. So at low pH, everything should be a positively charged something to some extent, because you really only have things that are neutral, like the carboxylic acids have the hydrogen on them, so there's no charge, or the nitrogen side groups have a proton on them and they're all +1. Okay, so you got a lot of positively charged things, and then as it keeps moving and going through this pH, as it's increasing the pH going through the gel, you're deprotonating some of those functional groups, and it's going to stop moving, right, once you hit the point at which the pH in the gel is equal to its isoelectric point. Okay, so a protein that would stop here around, have a PI of about 3, sounds to me like it probably has a few or a lot of the lower pKa side chains, so some Ds and some Es, and maybe throw in a couple other, like a histidine or a cysteine or two, but that's going to have a low PI. Proteins that tend to have a really high PI tend to, like a 9, tend to have more of those positively charged side chains, so more arginines, more lysines in them. Okay. So you always have to have a sample, right? So a sample question for an isoelectric focusing gel would be, how would the following mixture of protein fragments migrate on an IEF gel? That stands for isoelectric focusing. Okay, so we've got rafting, craps, angels, and angles. My brain, oh, that LE or EL. There's a few things my brain can't figure out. It's my left and right. I don't know which way is left or right. And then the other one that's just really funny is the greater than or less than sign. That one gets me every time too. I have to like slow down. So sorry. Angels and hark. Angels, hark, craps, and rafting. So you have to determine, right? These are the fragments. What is the isoelectric point for each of those? Okay, so again, that's one of the tried and true ways that we calculate isoelectric point. So you pick you have to write down every single, okay, let me just, I'll try my best to do one. We'll do rafting. Okay. We should be getting very comfortable though with calculating isoelectric points. So if we do rafting here, remember I'm going to have, blue's not the best color, I guess. Remember we're going to have an N terminus here, that's a 9.5. And we're going to have a C terminus down here, that's 2.3. Right? So now I have to go through and see which amino acids have an ionizable side chain and what is the value of that. R, do we have to worry about it? Yes, we do. It's 12.5. A, we don't care about. F, we don't care about. T, we don't care about. I, we don't care about. N, we don't care about. And G, we don't care about. So we just have 3 to worry about, right? Put that in increasing numerical order. 9.5, 12.5. And then think about at pH 0, what's the protonation state? Is it +1, -1, or neutral? The N terminus being an amine at pH 0 should be, I've lost my mouse, will be +1. The arginine R as a guanidinium side chain, which is nitrogen containing, so it'll also be +1 at pH 0. And the C terminal carboxylic acid will have the proton on it and it'll be neutral. So overall at pH 0, my charge will be +2. Then that means this would be +1. Here's my 0 point, and that would be -1. So the isoelectric point would be the average of 9.5 and 12.5. So it's 11. Okay, you got to do that for all of them. Obviously, by the time the exam rolls around, you need to be able to do this pretty quickly. So you've got to get really comfortable with those pKa values and what's the charge at essentially pH 0 and sometimes at pH 7. Like most questions tend to be around physiological pH or something like this where you're calculating the isoelectric point. And this is the best and fastest way that I know how to do it. All right, so you calculate the PI and then all you have to do is plot the PI. There it is. Sorry, my cursor's completely gone. Okay, then you just have to calculate the PI and then you plot them. So the PI of 11, that means it's going to stop at pH 11, 9 stops at 9, 3.2 stops about 3.2, and 11.5 stops at 11.5. Oops, clear. Okay, then we get even a little more crazy. So we can do what we call two-dimensional gel electrophoresis. So far, all the types of gel electrophoresis we've been talking about, we're considering one-dimensional because we're just going to run only down the well one way. Okay. 2D gel electrophoresis couples or combines the isoelectric focusing with SDS page gel. Okay, so what you'll see is you have your protein extract or your mixture. You run the isoelectric focusing gel, and so that little slab of a gel. And so remember, the proteins are going to separate based on their isoelectric point where they're neutral. You can then take that slab of a gel and put it on top of an SDS page gel. And then you can kind of like bind the two together. And then you can run on the second dimension the SDS page. So in the first dimension, the proteins are separated by the isoelectric point. And then in the second dimension, they're separated based on completely on their mass to charge ratio. So big, heavy proteins are up here. Smallest proteins run farthest down the gel. Yes, I have had questions on previous exams that were like, take these fragments and run them on a 2D gel. You might find one of those in a previous exam too, but you can make up your own peptides and do it with some people from class and check your work, check yourselves, right? So isoelectric focusing, you're gonna have to calculate the PI and then say about where it is there. And then when you run it in that second dimension here, you just know that the heavier, bigger molecular weight proteins stay towards the top and the smaller ones travel further through this mesh-like network. Look, here's the sample question right here. Who would have thought? I forgot I did this. Okay. How would the following mixture of protein fragments migrate in a 2D gel? So even notice here, I've got increasing pH this way. So pH, think like 2 over here and 12 over this way. And then increasing molecular weight. Man, that was really nice of me to say that. I should just probably say SDS page this way. So you'd have to remember that bigger proteins, actually that's actually wrong because it should say decreasing molecular weight down. Where's my draw tool? Decreasing, right? Decreasing. Big guys stay up here. The tiny guys go down here. Okay, so how would these three fragments run? I've got Cakes, Dad, and Hale. Let me see quickly. Did I mock calculate things? Just trying to get off of this annotation. Nope, I didn't mock calculate things. Okay, so you're going to have to, this is what you can do as a fun assignment, right? Calculate the isoelectric point for each of these. And then I can tell you where things are going to run relative to each other on the SDS part, right? Heavier proteins have more amino acids. I've got one that has 5, I've got one that has 3, and one that has 4 amino acids. So with this protein Cakes, is going to be a heavier one. So Cakes would run high, Hale would be next, and then Dad, right? So this is Cakes, this is Hale, and that's Dad. And, again, because you've got decreasing, not increasing, decreasing molecular weight going down this, but you need to calculate the isoelectric points and then figure out where that goes on the scale of, about from 2 to 12. So how those would separate there. Okay, so that sums up the types of electrophoresis. So we covered native page, SDS page, isoelectric focusing, and then 2D gels. So the two-dimensional, so it couples isoelectric focusing with SDS page.